Welcome. In this lecture, we're going to answer the question from last lecture about how are the antiderivatives related, and then introduce the generalized antiderivative. Okay, so let's start with what I might call like important facts or a theorem. So here are some important facts. So this is a theorem. Okay, the first one is that antiderivatives are never unique. I'm going to write this in green because we're talking about antiderivatives. So, I was making them red before. Let's do them in red. Okay. Okay, so here we go. So, antiderivatives are never unique, so antiderivatives are never unique. And, right, because we could add a constant, and that's all you can do. Otherwise, they're the same, okay? So they precisely differ by all constants, okay? So they, meaning antiderivatives, precisely differ, like for the same function, they differ by all constants. So I could add any constant to my antiderivative, and it's still an antiderivative. And then the other way is that that's the only way to get between antiderivatives for the same function. Okay? So this kind of spikes or prompts us to create a definition. So we call, if I take this f, so I take any antiderivative, and then I add c, okay? We call this a generalized antiderivative. Okay, so call this a generalized antiderivative. Generalized. This is a little too light. So a generalized antiderivative. Okay, so this is kind of a new word. I'm going to box it in red anyway. Really going to use red for both of them. Okay, so let's kind of draw the picture. So let's and go through kind of an example. So here's my example. So if I have f of x equals x plus 3, then, right, so what should my generalized antiderivative be? Okay, then f of x equals, right, oh, that's not x plus 3. Let's see, I took the antiderivative wrong in my notes, but it was that I wrote this down wrong. That should be a 3. Then f of x equals 3x plus c. Okay. Is a generalized antiderivative. So this is a generalized antiderivative. Okay. And what does the picture look like? So it's like I have my x-axis and I have my y-axis. And one of those would be the one that goes like right through the origin, right? Like this, right? So this would be one of them. So this is like y equals 3x, right? But I mean, here's another one. Right, if I add a constant, these are supposed to be parallel. I think I failed a little bit at that. So I could do y equals 3x minus pi, for example. Or I could do, right, I could do y equals 3x minus e squared. Okay. I could also do something like I can add right? I could do y equals 3x plus e. Okay, and so this is what we call, this is like a family of antiderivatives, right? So this is a family of antiderivatives. So it's an entire set, right? When I'm talking about the generalized antiderivative, I'm actually talking about an entire set. Okay, so it's a family of antiderivatives. I tried to, in an attempt to get it all squeezed on here, I made it way too difficult to read. So derivatives. Okay. And so the kind of important thing is if I had drawn this correctly, so note that these are all vertical. So note, these are all vertical translates of each other because you're adding a constant. So they're all vertical translates of each other. So there's infinitely many. It's all of the translates. It's precisely the vertical translates, because that's precisely what happens when you add constants, right? Or another way to think, they're all parallel. Okay, so just to kind of recap, we talked about one antiderivative. We talked about the fact that, like, you could add any constant and get the same, you know, and you'd get another antiderivative, because when you take the derivative of a constant, you get 0, right? So that part just kind of drops off. And we can kind of think about those all at once, like as a set or a family of functions. And that's the generalized antiderivative. It's kind of cool in the picture that they all are vertical translates of each other because they're all adding constants to each other. And it's precisely all the vertical translates. These would be parallel if I could draw correctly. So I hope that made some sense, and I will see you in the next lecture.